Okay, yeah, please, Vesti, whenever you're ready.
Okay, let's continue. So as you probably remember, we start discussing this normalized generalized Ricci flow on toric Thanos and joint work with Jeff and Yuri. And in the first lecture, just give me a second because I have a slight technical problem. Okay. Yeah. So in the first lecture, I cover very few of a small portion of what I was supposed to. So we essentially did some general remarks about scour reduction of Ricci flow and some abstractions to global existence of generalized Ricci flow. So today there is a lot of material to run. So we saw last time the main motivation for us is to consider Fano because we can solve this cohomological abstractions to long time existence of the generalized Ricci flow. And more specifically, if you consider a J-fixed gauge, to consider the normalized generalized Ricci flow by the equation you see, then the main observation from last time is that the Aptly class stays fixed if, so let me see, if the initial Aptly class is exactly in this normalization to P kappa C1. So under this normalization, we saw that there are no abstractions for long time existence, and therefore we hope to get such long time existence result. So one assumption that we discussed last time is that we will be interested in generalized scalar or Hermitian structures of symplectic type. By this, we mean that there exists a symplectic form, a globally defined closed two form, which tames the two complex structure in the Hermitian pair, or equivalent in the 1-1 part of this two form with respect to I or J, gives the corresponding fundamental two forms. That's what's called of symplectic type. And we observe that actually this form alone fixing J and a symplectic form, which tames J, actually determines the other complex structure automatically. If this other complex structure is also integrable, we will have automatically a generalized scalar structure where H will be given by the skew symmetric part of F composed with J, and the Riemannian metric will be essentially the symmetric part of minus F composed with J. So we can think of the space of generalized scalar structures of symplectic type as a space of two forms on our manifold, which are symplectic and whose 1-1 part is positive definite. So these are nice convex conditions, linear conditions, but we also have to impose that the almost complex structure, which is the conjugate of the fixed complex structure with respect to F, is integrable. So the second condition actually is nonlinear. So from that point of view, this space doesn't have a natural structure of Frechet space. So this was done last time, and the main observation is that actually this J fixed gauge, generalized scalar Ricci flow, or the normalized version of it, would fix the condition being of symplectic type. This means that if we start with something of symplectic type, then we can, so the claim is that it stays of symplectic type, and actually the corresponding symplectic forms will evolve by this equation. So you could think of this equation as defining the symplectic form, which is one way to think, but then remember that along the generalized scalar Ricci flow, we knew that, okay, so probably we knew that L theta I minus theta J So I point. The second complex structure involves in a certain way. So the claim is that this complex structure here will evolve exactly by this equation. So this proposition is not entirely vacuous, so you have to check something. Okay. So then this symplectic type condition is preserved along the flow. So we'll be interested of a situation where we start from a generalized scalar structure of symplectic type. So the flow will stay symplectic type, and then we want to think of what we are doing in the following terms. So this along the flow, you have this symplectic forms Ft, which are on the fixed homology class, which is just 2pc1. And for each given form like that, it will define a volume form. So this volume form is strictly positive because Ft tames the complex structure J. And we can solve by Yau's theorem the equation omega bar T m is Ft for a unique Keller metric in the same Keller class, in the same homology class. So we have a associated Keller metric omega bar T. And the idea is that this associated Keller metrics omega bar T, they will vary in a fixed Keller class and therefore can be written in terms of a scalar function, which we call the relative Keller potential. And therefore, this normalized generalized Keller Ricci flow of symplectic type is somehow reducible to a flow of potentials, to some sort of a parabolic scalar PD for these relative potentials. Of course, this is too good to be simple and nice and true in full generality. The problem is that we cannot define this object explicitly, so this is implicit. So in general, even though this is possible, it's not easy to see exactly what kind of PD this scalar reduction will satisfy. But we will today we will see that all this works very nice if we assume that our Fano manifold is toric. So by definition, a toric manifold is or Fano toric manifold is a Fano complex manifold, such that the group of automorphisms contains a torus of dimension half the real dimension of the manifold, which also is a maximal possible dimension of a compact torus. And in this case, the two main results that I want to discuss today are these two theorems. So the first says that if we start from a generalized scalar structure of symplectic type on a toric Fano, then the flow will exist for all time. So this will be the analog of the corresponding result by Tsao in the Keller case. And the second result is more technical, but it essentially says that if we knew that this toric Fano was Keller Einstein, then there is some sort of weak convergence of these potentials phi t. I will probably make more precise statement when we come to discuss this theorem at the end of the talk. But the convergence is in sense of currents, and you have to also gauge with any given time with the action of the complex automorphism group of the Fano manifold in order to obtain this convergence. So these are the two main results that I will discuss. There is another result in our paper, which I am not going to discuss today. So this is kind of a simplified version of it. It's without any toric assumption. It's that if you have this normalized generalized scalar Ricci flow on a Fano manifold, and it's of symplectic type, and if ever it converges to something, then this something is necessarily a Keller Ricci soliton. It will be a Keller structure for which the Ricci form minus the Keller form is a 1/2 DDC of f of a smooth function f, such that the gradient of f is a holomorphic vector field. So this is another thing that we observe in the paper. Okay, so for today, my main objective is to explain you why in the toric case we can really prove this long time existence and reduce to a scalar PD. So I will start with some general discussion on Keller toric geometry, no final assumption at the beginning. It's a kind of a classical and well-known material going back to Giemann and Abreu, and with some important supplement by Donaldson more recently. So here is the setting. So we start with a symplectic manifold, compact symplectic manifold with effective action of a torus of how the real dimension. So Hamiltonian means that we have a TM invariant moment map. It's a smooth map from the manifold to the dual of the Lie algebra. We are in the billion category. So this dual Lie algebra is just a vector space. And a central result in this theory is an old result of Delzahn, very beautiful result of Delzahn, which says that in the above setting, the image under the momentum map of the compact symplectic manifold is a compact convex simple polytope in that vector space, which you could parameterize this polytope as intersection of half planes in a intersection of hyperplanes, if you want, in an effective way. So each equation counts for something. So I will write the polytope as just an intersection of inequalities of this form, where Lj is an affine linear function. And the Delzahn condition is that the normals, so these normal vectors which define the affine functions, so each Vj, we can think it as the differential of Lj. So these normals, they lie in the dual space of where these affine functions are defined to. So these are elements of the dual of the Lie algebra. So this will be elements of the Lie algebra. So these normal vectors, they have to be a lattice vectors. In other words, they have to lie in the lattice of circle subgroups of your torus. So that's one condition. Second condition, which is related with this simplicity, is that if you look at the defining hyperplanes, which contain a given vertex of your polytope, there will be exactly m of them. That's what means simple. And these normals, so you have an m normals corresponding to each vertex. You want these m normals to form a z basis of the lattice. So there is some integrality condition associated to this polytope, which is called Delzahn condition. And the beauty of this theory is that conversely, if I give you a polytope in Rn with these properties, it will define a symplectic toric manifold. And actually, what's interesting to observe is the way it defines a symplectic manifold is by reduction. For instance, if I take a simplex, so this will be a Delzahn polytope in R2. What you will do, you will essentially consider the defining, you will have three defining facets of this polytope. So you consider C3, the vector space freely generated by the normals, and Delzahn prescribes a procedure to obtain the symplectic manifold as a Keller quotient of C3 under the action of some torus. It will be in this case S1, and you will get, of course, CP2. So this Lausanne theorem, it's important to notice is that it also gives you for free an induced canonical complex structure and induced canonical Keller metric on your symplectic manifold, because it's realized as a Keller reduction of some CD, where D is the number of defining affine hyperplanes of your polytope. So this fact was used by Lausanne initially to prove that any toric symplectic manifold is also toric projective manifold. But I think Giemann pointed out that this fact can be also used to describe in a very effective way the space of all invariant Keller structures on such manifolds. So what we'll be interested in now is to describe all T-invariant complex structures J, which are compatible with the initial symplectic structure. So this is the symplectic point of view. We fix a symplectic manifold and a torus and a momentum map and momentum image. And then what will vary is the space of omega 0 compatible almost complex structures which are integral. That's what we call a Keller structure. So this is a Keller structure. Because given the complex structure by omega 0 compatibility, you know that the Riemannian metric is just obtained by composing symplectic form with J. So how to describe this space? So there's a very simple argument essentially. So we start with so we would take generators of the torus action. So we'll take Tm will be S1 n times, and Ki will be a generator of each factor. So I have m vector fields. Each of them will generate let's say S1 factor in your torus, and they will form a basis of the Lie algebra. Okay, so these vector fields will be they will be independent not on the entire manifolds, but on a dense on the subset of generic orbits for the action, and they will correspond to the pre-image of the interior of the quantum. So these vector fields will be independent on the regular part for the action, which is just the pre-image of the interior by the Lausanne construction. Can check this explicitly. And if I take these m vector fields, I can use a compatible omega 0 compatible complex structure, which is invariant, to complement them. So I will complement these m vector fields by twisting with the complex structure. So now I'll get two m vector fields. And because J is integrable, we will have that the Lie bracket of chi I and jkj will be 0. Actually, this follows by invariance. And because it's integrable, I can also write that j kj is 0 by using the integrability. So as you see, we will get now a basis of two m vector fields of the tangent space, which will commute. So we have a Frobenius basis, and the Frobenius basis gives you local coordinates. So I will denote these local coordinates by θ1, θm, and y1, yn. And you can immediately see that these are actually pluriharmonic coordinates, which means that θi plus square minus 1 yi are holomorphic. So in particular, the complex structure, let's say G star in this coordinate base, will have a very nice form. It will be canonical structure. It will be given by minus identity. So what about the metric? How I can describe the metric in this coordinates? To describe the metric, we can we will introduce just these quantities G, Ki, Kj. So this will be a symmetric component of a matrix, which kind of a matrix of smooth functions on the manifold. And because the construction is torus invariant, if I take the derivative of this matrix by any of these vector fields, it will give me 0. So this H is really a function only on Y, symmetric, as we said. And the compatibility condition that we imposed on J tells me that G is a Hermitian metric. If I mix Ki with JKJ, this is the same thing as omega Ki and Kj, but omega Ki is minus d mu I applied to the Kj. Since the momentum map is invariant under the torus action, this will be 0. So there will be no mixed terms. So the conclusion of this thing is that we get in this pluri-harmonic coordinates or holomorphic coordinates, the complex structure is very, very simple. And the Riemannian metric is of this form. And by compatibility, the symplectic form will be written like this. So you have you could write down completely the Keller structure in these coordinates. But it turns out that it will be convenient to do something else. That's what Gilman did. Instead of using this natural holomorphic coordinates, there are other natural coordinates, and namely the momentum coordinates. So I will use the theta's coming from the above construction, but we'll replace the y's with the mu's. You could now figure out how this goes. So the first observation is that I can express the mu coordinates with respect to the y coordinates using this observation that the mu jkj is hij. So essentially from here you get here, and from there, and using this, you will get this observation that actually omega 0 will become so actually mu j and theta j will be Darboux coordinates for the symplectic form. However, I want to stress that in all these discussions, these thetas, they depend on the complex structure we started with. So in current language, mu and theta j are called momentum angular coordinates, and these coordinates are natural from the point of view of symplectic geometry because they are Darboux coordinates for omega 0. Now that these Darboux coordinates are very natural, essentially is seen by this lemma due to Gilman, which tells you the following thing. So if I introduce the inverse matrix of Hij that I just defined before, then this inverse matrix will be a Hessian of a function, of a convex smooth function defined in the interior of the pointer. And this function is important, play an important role. It's called symplectic potential, Gilman potential sometimes. So here is the proof. We saw already that, okay, so this is Hij, and this is Gij. with Gij, the inverse. So how we can prove the statement? So we saw that in the initial holomorphic coordinates, we will have dyj is g star d theta j. And we saw how this changes in momentum angular coordinates. So g star d theta j will change in this precise way. Because of that, because of this relation, we can define a one form. Alpha will be a one form, which we define essentially on the Lie algebra, on the polytope. And the relation that I just wrote shows us that alpha is closed, because if I write the alpha, so the alpha will be dy I d mu I, but dy I is Gij mu d mu I d mu j. And now Gij is symmetric. So this is symmetric. And because of that, this will be equal to 0. So essentially, it's almost obvious that this will be closed forms. These closed forms are defined in the theory of the polytope. The polytope is convex, simple, everything. So the interior is simply connected. So you could use Poincare lemma to write each one form. This one form, I can define it as, I can write it as d of a function defined in the interior of the polytope. And now developing this and comparing with this definition. So alpha is that. From this definition, you get Ej is equal to the derivative of y with respect to j. And now we will plug in the first equality. So in develop, and you get that's the matrix Gij is precisely the hash of this function u. So it's essentially a Poincare lemma. This observation of Gibbon. Gibbon gave a slightly more different and more complicated argument using a Didi-Bar lemma, but it really goes as simple as I just explained. It's a Poincare lemma on the interior of the polytope. So the conclusion of this is that we can describe these scalar metrics in terms of functions. So u will be a well-defined smooth functions on the interior of the polytope, and it will be strictly convex because these have to be positive definite matrices. The Hessian and the inverse Hessian have to be positive definite in order this to be a Riemannian metric. So then, starting from this remark, there was further development. People start asking, well, that's on the interior of the polytope, or if you prefer, on this M circle, on this regular part of this dense open subset in your initial manifold. So the next question is, what would make it this to become a globally defined kind of structure? And this has been answered in different steps. So the first observation was due to Gilman, who explicitly write down this induced canonical Keller structure from Lausanne construction. So Lausanne realized, given a polytope, Lausanne consider a Keller reduction of some complex space with respect to the flat structure. That's why he proved that there exists at least one compatible Keller structure, and Giemann explicitly found what is this symplectic potential for that particular structure, and it's shockingly beautiful. It's just the sum of 1/2 Lj log Lj, where Lj are defining affine functions. That's what Gilman proved. And of course, as I said before, for each omega zero compatible Kähler structure, you have induced angular coordinates. So there are also angular coordinates coming from this canonical Lausanne construction. So so Gilman found this beautiful formula of the precise form of the symplectic potential. And then Abreu started, and I think himself and Donaldson gave a slightly different flavor resolution of the problem of what would look like some other globally defined T-invariant omega zero compatible Kähler structure. So we know on M0 or on the interior of P, you have this symplectic potential, but what are the boundary behavior of this symplectic potential in order to define a global object? That's the question. And here is the answer. I am stating the Donaldson version of this. So if you look at Abreu, you have to look at, well, he wrote two or three papers on that. You have to look at the last paper. It is the one that is complete. But these conditions are due to Donaldson. So they say the following thing. So this structure, arbitrary structure, is global if and only if the corresponding symplectic potential differs from the canonical one by a smooth function which is defined around P, in the neighborhood of P. So it's extendable smoothly. And you need a second condition, namely that this U, if you restrict to any face of the polytope. So any face is itself a Lausanne polytope of lower dimension. So you have to be able to show that the restriction on the interior of each face is smooth and strictly convex. So if you combine this comparison with a model plus the convexity on each individual face, then you could extend, or if it comes from a global object, it will be true. And furthermore, in this argument, it's important to notice that actually we can assume to the action of the diffeomorphism, global diffeomorphism groups, that the angular coordinates of these globally extended toric Kähler structures are essentially the ones given from the canonical reduction. So you see the group of T-equivariant diffeomorphisms acts on the space of Gj. So it acts on the space of angular coordinates. And what it says is that the action is transitive. So you could always fix them as you wish for one given global object. So we will use the global object corresponding to the canonical structure, and then we could, up to this action, parameterize the pairs of metric and compatible complex structure with essentially symplectic potentials and these fixed angular coordinates. So I will probably put this in some sort of a conclusion.
Can I ask the question?
So there exists a bijection between strictly convex smooth functions defined on the interior of the polytope, satisfying these two boundary conditions. So U minus UC, U minus model, smooth, and U restricted on the interior of each face is strictly convex and smooth. So this condition is defined up to adding an affine function, as you could see immediately. So adding a affine function to U doesn't change the metric because we take Hessians. So you have all these functions modulo addition of affine linear. And on the other hand, you have isometric classes of T-invariant Kähler structures modulo omega zero.
Right, Vesti, can you hear me? Can you hear me okay, Vesti?
And this object U is called symplectic potential. Yes, Mark.
Can anyone else hear me?
Can you hear? Vesti, can you hear me?
Sorry.
I don't hear you. Probably I'm mute.
Testing.
Yeah. Right, I hear you now.
Oh, okay, so
sorry.
Jeff, you should ask now.
Yeah, okay, sorry, Vesti, I had a question. I was just curious if there was sort of I don't know, a conceptual reason why there's no condition required on like the higher codimension faces of the polytope?
It is on any face. It's also on
sorry,
higher.
so when you say face, you mean every lower dimension?
Face is every, face set is codimension 1.
That doesn't mean codimension 1, that means every codimension?
Yeah, face is every codimension.
Okay,
face set is a codimension 1.
I see. And sorry, just so I'm clear, and the condition was on the faces.
On the faces, on the interior of each face. Yes, absolutely.
Okay.
Yes, 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 yes.
Okay,
yes.
Thanks.
Yes, by the way, this second condition is very often overlooked in even in serious papers. So that's one kind of a tricky point of the theory. But yeah, it must be. In a Brio formalism, he places a condition on the determinant of the Hessian. So that's an equivalent way. So you have U minus UC smooth, and the second condition will be the determinant of Hessian of U over determinant of Hessian of UC, smooth and positive.
Okay.
So that's an equivalent way to express this. You could do that. They're equivalent. And then there is a third way as well. It's a first order kind of, but that's a little bit different twist on the theory. Yeah.
Thank you.
Can I ask a question?
Yes, absolutely.
Are the symplectic structure associated with Deleuze polytope and the complex structure, I mean, individually, there's only one isomorphism class, and the function just picks out kind of a way of putting them together? Is that right?
So in that picture, the symplectic structure is omega 0, it's fixed. So you move the almost complex structures. So you're probably referring to the fact that now these integrable almost complex structures are biholomorphic as well. I will discuss this in a moment, so probably answer your question more naturally. So just continue, and you will probably ask me again if it doesn't answer. But in this theorem, symplectic form is fixed. The only thing that is flexible here is essentially the pair of remaining metric and compatible complex structure, compatible with that fixed symplectic form. And the other thing that's flexible a little bit are these angular coordinates. But we said that part of the theory is to show that that they can be fixed too, breaking the action of this equivariant symplectomorphism group, which is a very big group. You could fix them as well. Then this will be up to isometry. You have the whole space. Yeah. So now, what about Keller potentials? You remember the first lecture we said that we wanted this phi function, which was a smooth function on the whole manifold, and this this symplectic potential is definitely not a smooth function on the manifold because it has the asymptotic of this Lj log Lj. And that's not a smooth function, it's only a continuous function. So this U is not the old object or the object that I wanted to introduce. So how to define this relative Keller potentials, which will be called as smooth functions on the manifold? So here is probably the answer of the question of Francis. I think it was written at least black and white by Lerman Tolman, although certainly known by two experts before that. But in this formalism, the Gilman-Brio formalism, any T-invariant omega 0 compatible Keller structure, actually, if you just look the complex structure, it will be biholomorphic to, let's say, the canonical one. So each two complex structures are biholomorphic to each other by some T-equivariant diffeomorphism. So this time, this equivariant diffeomorphism will move the symplectic form away. So that's the catch. So in particular, I lost connection. Okay, I think it's okay. Yeah, my tablet lost connection. Sorry about that. See what happens. Okay. Yeah. So right. So I guess yeah, that's the point. So Lerman and Tolman observed that actually you could map any given globally defined complex structure coming from omega zero compatible guy to the canonical one via some diffeomorphism. And what will happen is that the symplectic form will move away. So this symplectic form omega zero will move away, and you will introduce a new symplectic form, which this times will be JC compatible. So it will be a symplectic form compatible with the canonical complex structure, almost complex structure, and therefore it will differ by DDC of a smooth function. So our relative potential will be this smooth function, and I want to express this object by this symplectic potential that we introduced before. Okay, so that's the next step to see how this works. So in order to do that, we will first use the structure theorem before in order to move the angular coordinates. Remember that the angular coordinates, they were defined by the starting almost complex structure, but the structure theorem of Abreu-Gilman tells us that we could actually move one pair to angular coordinates to the canonical one without changing the symplectic potential. That's what we'll do first, and we'll ignore this first step. Once we have assumed that the angular coordinates of this J are the standard, the canonical ones, we have a U, it turns out that the relative Keller potential can be obtained in the following way. So we will do the Legendre transform essentially. So what we do, you will take the partial derivatives of U, given the symplectic potential U, and we will rediscover the holomorphic coordinates Y. YU, they will depend on U. And what we will do, we will just map in that position, we will map the holomorphic coordinates YUJ, TCJ to the canonical holomorphic coordinates. So this process is only well defined on this open dense subset of the pre-image of the interior of the polytope. It's not at all clear that this mapping is well defined globally, but Donaldson actually made a thorough argument that this diffeomorphism actually do extend because of the boundary conditions on U. So you could work with these two boundary conditions that we put on U to show very explicitly that actually this diffeomorphism extends in an equivariant way over the pre-images of other faces. Essentially, it extends to equivariant diffeomorphism globally. So this is perhaps the answer of Francis' question, that actually if we want to identify the complex structure as a canonical complex structure, then we'll move away the symplectic form. And actually, we can identify this complex structures in a very controlled way, in a canonical way, up to changing the angular coordinates. And then at this point, we'll go back again to Gilman's initial approach. He just observed, and it's very easy to check, actually, from what we said before, that if we now introduce the Legendre transform, so we have U, which is a strictly convex function, we introduce these coordinates by the gradient of U, and we will introduce this version of phi U, this function, which will be the Legendre transform of U. Then you could check immediately that under this you get a general expression of the symplectic form as DDCJ of this Legendre transform. So the Legendre transform of the symplectic potential is a Keller potential, once again defined only on M circle, on the regular part. But from what we said before, by this Donaldson canonical diffeomorphism, if we combine the two arguments, it will give you actually that the image of this initial Keller form under this canonical diffeomorphism, it will just replace YU by YC here. So we will get a DDC JC VU YC. And from here, as Donaldson observed, this relative Keller potential will be just the difference of the Legendre transform of UC, actually Legendre transform of U minus Legendre transform of UC, seen as abstract functions, and then put on the manifold via the canonical holomorphic coordinates. So that's the simple calculus that gives you this globally defined smooth function on your manifold, var phi. So here is the upshot of this discussion. So the Legendre transform, which is just a transformation of a one convex function to another one, also changing the variables, corresponds to a geometric operation, namely to start with a T-invariant omega-0 compatible Keller structure, modulo equivariant symplectomorphisms, because we need to fix the angular coordinates. And this set is mapped by Legendre transform to the space of T-invariant Keller metrics in a given Keller class. But there is a catch. The catch is that if I replace, so in the first space, U is only defined up to adding a affine linear function. If I add a affine linear function to U, you will see immediately that YU will change. Actually, we will add a constant to YU, and therefore this canonical automorphisms will change too. But adding a constant to Y is essentially comes from the action of the automorphism group. So geometrically, what you see is that you have a bijection of the first point of view to the space of T-invariant Keller metrics in a given Keller class, but modulo the action of the complex torus this time. Because this Y is essentially so this YC coordinates corresponds to, you exponentiate them to get the action of the C star on M ring, on M0, on M circ. So these 2 points of view are not the same, but there is a precise dictionary how to go from one to the other and vice versa. So that's it. Are there any questions at this point?
Could I ask on the last slide?
Yeah.
What was, like you had, like was it, were you comparing omega with JC to omega-0J, or was it the other way around?
Yeah, so maybe it's here. I'm comparing the image of omega-0 by this phi c with omega. So the difference of omega minus omega-0 is a DDC var phi u. Probably that was written in here. So right, so essentially this calculus comes from two sources. The first is this observation by Donaldson that this is globally defined because of the boundary conditions, and the second observation, which is local in nature, is this very nice formula given. Actually, he observed that the Legendre transform is a Keller potential for the symplectic form with respect to the complex structure we consider. So if we put these observations together, we arrive at this expression, this magic expression. Okay. So now next step is to do this in the category of generalized Keller structures. I really wish to try probably to have 2 minutes break, and we'll try again to connect my tablet because I want to
Yeah,
write.
sure.
So just
Recording, okay. Yeah.
Okay, so so now we want to do something similar in the generalized scalar case, and that's work first by Boulanger with an important supplement by Wong more recently. So here, what we will do. So we will start with generalized scalar situation as before. We will assume it's of symplectic type. So we have this f. F will be our symplectic form now, and we will fix it at the beginning. So you have the momentum coordinates again, fixed, given by the initial setting, and we will have again, exactly as in the previous discussion, in the Keller case, we will have a pluriharmonic coordinate just by supplementing with this K1 Km with JK1 and JKM. So this gives me 2M commuting vector fields on the regular part and circ. So now, what is not precisely the same is the following. So the first observation we will make is that what we did before, we introduced this function hij. How we introduced it, it was essentially given by, let me see. It was given by this, before was hij, which was symmetric. So now there is no reason to believe that this is true, because just J and F are not compatible. So if we compose F by J, it will have a symmetric and antisymmetric part. So this will be not longer true. So that's the first observation. The second observation is that well, so still we can do something. We can, for instance, I have dropped almost this connection today. I think I have again freeze connection for some reason. I will switch for the computer talk and I will not denote. Sorry about that. We said that this. So we said that this guy is no longer symmetric, but still I can use I can express the integrability very in the same way, even if it's not symmetric. So this is the inverse metric. So Cij is really Cij will be the inverse of that quantity. So Cij upper indices will be this. It was H before, and Psi will be the inverse, which was G before. So I just did the notation at once. So exactly as we did in the Keller case, we can write that G star of this J angle, well, J holomorphic coordinates theta is given by Cij d mu I, and if I take another derivative, it's precisely equivalent. Will be equivalent to the integrability of the structure. So you get a similar relation as before for the integrability of J expressed in terms of this matrix. So that's the first difference. The second difference, which is actually more dramatic, is that we cannot claim anymore that theta j and mu j are Darboux coordinates anymore. If you remember, in the Keller case, we used the fact that the J star was anti-diagonal with C and C minus. This will be again the case, but we had to use the special form of the Riemannian metric, which was also tied to this H matrix. This will be not longer true. So you cannot claim in general that these are Boole coordinates. But if we imagine for the moment that they were, imagine that we knew that omega is d mu j wedge d theta j. Then this means that the matrix of omega in these coordinates is very simple. It will be identity minus identity of diagonal. And we can compute very easily I, because I, if you remember, it was just obtained from J and F by conjugating. We have to take F minus 1, J star, F minus 1. If F was very simple, as I said, then we could do this conjugation. We will find that I will be will correspond to psi transpose. I will correspond to the same psi, but with G and I inverted. So that's what Boulanger observed. So he said, well, let's assume, let's consider a subclass of generalized scalar structures of toric type, for which these are their Boole coordinates. Then the integrability condition for I will be the same, but with psi transpose instead. And then this is a linear condition. We can take symmetric and antisymmetric parts individually. For the symmetric part, the same argument as before applies. So we'll have a symplectic potential coming from the symmetric part of psi. And we have also a similar integrability condition for the antisymmetric part. But the elementary linear algebra shows that this integrability condition for antisymmetric part just means that psi antisymmetric ijk is 0. So it's a constant. And that's what's called this Boulanger ansatz. We call it A-type deformation. It says the following thing: if you have a symplectic potential of a F-compatible Keller structure, so this symplectic potential will define a Keller structure different from the generalized Keller structure we started with. So we have such a symplectic potential with angular coordinates theta j, and we take some anti-symmetric constant matrix A. It's just I would think of it as an element of lambda 2 Lie algebra. Then we can let Cij be the Hessian of U plus this constant matrix. Then this precisely corresponds to integrability condition of I as well, actually. So then the observation is that we'll have a generalized scalar structure which will be compatible with the starting symplectic form, and which will have I and J will have the same form in this momentum angular coordinates, but with psi replaced by psi transpose. So the remark here is that the Boulanger's construction really is if and only if construction if you impose this extra assumption that mu and this theta part of the homomorphic coordinates are their Boole coordinates per case in the Keller case. So we call this A-type deformation. So this construction allows you to start with a symplectic Keller as before, and to take this constant matrix Aij and construct a new kind of a deform this to get a generalized scalar structure of symplectic type. They will share the same symplectic form, the Keller one and the deformed generalized scalar. So this is the Boulanger, and more recently, about 2 years ago, I think, Wang actually made a very ingenious remark. Actually, he understood what was missing in Boulanger's story. So of course, this condition of imposing their Boole coordinates was unnatural in a certain sense, and his observation is quite quite remarkable, I would say. So now we start with a deformation in the Boulanger sense. So generalized scalar with this extra condition imposed. So we know that it corresponds to a honest scalar structure corresponding to a symplectic potential and a constant but antisymmetric matrix. This A-type deformation. So what one observed is that now we can deform the symplectic form instead of the complex structure. We just take this. So remember, in Boulanger construction, the symplectic form and the Keller form, they were the same. They didn't change. But now we would change this symplectic form F, starting symplectic form F, by adding this expression. I do think I saw this during the Francis talk, this type of deformation. I will probably comment this later on. But yeah, that's how we would deform now the symplectic form. And his observation is that, and we'll do nothing about the complex structure. The complex structure J will stay as it was deformed by Boulanger. So his observation is that as far as this deformation of symplectic form still tames J, the conjugate, the other complex structure obtained by conjugation, will be automatically integrable. And this corresponds to the fact that we deform by something constant. So essentially, now the taming condition will impose some constraint on this constant vector, 2 vector. You want this to be, so the 1 part with respect to the JUI has to be positive definite. So for small b's, this will be okay, but for if you multiply b by a big constant, this will not be true. But the integrability is automatic. And actually, if you see what are the precise angular momenta for this deformed form, you will notice that they do change precisely by this bij mu I. So he essentially corrected what Boulanger imposed as an ansatz. And the upshot of this is that these 2 constructions put together gives you the general form of a generalized scalar structure of symplectic type. So I will kind of repeat the whole thing. So any t-invariant generalized scalar structure of symplectic type can be obtained from successive A-type deformation and then B-type deformation of initial omega-compatible Keller structure corresponding to a symplectic potential U. And this actually is global. That's the most amazing thing. So you can work out the boundary conditions as was done before and show that essentially UE corresponds to a globally defined Keller structure, the symplectic potential that we constructed. And the condition for the precise condition for B is the following. Remember, for U was that U was strictly convex on the interior of each face. Now we will have the condition that the Hessian of U plus square minus 1B, this will be Hermitian symmetric matrix, what you get, will be positive definite in the interior of each face. And I remind you that elementary linear algebra shows that this condition is stronger than the positive definiteness of Hessian of U. So you need, so it's an extra condition on. I would think of it as a condition on B actually. Okay. So A is any. A is a constant 2 vector which could be of any size you wish, but B is constrained to this positivity condition on the interior of each face.
Sorry, Vesti, I think I'm a little confused about the hypotheses. I mean, like, are you assuming at the outset that omega naught is like compatible with some Kähler structures?
It is, yeah, that's the upshot. Yes. So this U.
Well, but that's like a consequence. You're not assuming, or are you assuming that?
This is an if and only if statement. So roughly speaking, I show you the one part of the story how to construct the generalized Kähler structure from a given omega 0 compatible Kähler structure. but their theorem is if and only if condition. Boulanger established this in 4 dimensions, and I think Wong supplemented. So they prove that this U exists always and satisfies the Gilman boundary conditions, Gilman-Donaldson boundary conditions. So hash and U is positive when restricted on an open face. That's what they prove. And moreover, what you have to figure out is that this condition that F is globally, that F tames J, it's another necessary condition. It's equivalent to this one, to the condition I put downstairs. I think we wrote it in our paper, this part of taming that's equivalent to this.
But I mean, you're saying I just assume T invariant symplectic type GK, and then in particular there exists a T invariant Kähler structure, and moreover, it's related in this fashion. Yeah,
that's the statement.
Yeah, okay.
So, right. The statement is that there exists a honest symplectic potential of a honest Kähler toric structure, and your structure is obtained by A and B type deformations from the Kähler one. B type deformation is constrained to this assumption on each. That's the statement.
Oh, sorry, I have a question about.
Yeah.
So I'd like to know some relation between these results and holomorphic Poisson structure on the toric Kähler. It's torus action. So that there are holomorphic vector field corresponding torus action. So by using this torus action, we can have a holomorphic Poisson structure. So that A and B can be constructed corresponds to such a Poisson structure. So I think, and so such a Poisson structure have the real part and imaginary part. But A is just maybe correspond to the real part. Deformation correspond to the real part of the holomorphic Poisson structure, and B is just the imaginary part of the Poisson structure, I think.
It's almost true, but not quite. You'll see in the next slide. So the first remark I want to make is that you have J and I in this construction, and you may wonder what it corresponds in terms of this data. So from now on, we will think of these generalized Kähler structures of toric type, symplectic, toric, whatever, as triples of a symplectic potential, a honest symplectic potential of a Kähler metric, and this constant antisymmetric matrices A and B, which we, as we said, are elements of the lambda 2 of the algebra. And as Professor got to observe, they somehow, on the background, should be related to this holomorphic Poisson structure. Okay. So what will happen if I change J and I? So you can see that from this explicit recipe, how to construct objects, that UAB will change to U minus I minus B. Okay, so the geometric symmetry of intertwining I and J will correspond to changing I and B by psi. And by the way, if we change B by minus B, this condition stays the same, because the positive definiteness of Hermitian symmetric matrix is essentially the same for the conjugate matrix. And here is the answer to Professor Gott's question. What is the link with the holomorphic Poisson tensor? I don't think this was computed, although the computation is quite hard if you get to the. So you should think of this A and B type transformations of something very explicit. We can everything write in whatever coordinates you prefer. For instance, momentum angular coordinates. You can write all the objects explicitly in matrices and compute everything you want. But somewhat long and tedious computation shows us that the holomorphic symplectic structure associated to this torics are given precisely by this formula. It's twice A plus square root minus 1B. And then you have to take K plus square root minus 1 JK, wedge KJ. So if you take the real and imaginary parts, they will involve A and B. It's not true that A is the real part and B is the imaginary part. But what is true is that you have this maximal real torus T, and in a certain way, this maximal real torus defines an additional real structure on your space of holomorphic Poisson vectors, and it's somehow related to that. If A is 0, for instance, you could see, if A is 0, perhaps you could express B from the imaginary part, but in general, they're mixed. So if you take real imaginary parts of this sigma, you have A and B in each. There is a nice symmetry. So on a toric manifold, the holomorphic Poisson structure does determine A and B completely, and that's a geometrical meaning of A and B, indeed. Another extremely pleasant observation is that you remember that these Ricci flows, general scale Ricci flows, we work with this Bismuth-Chern connection, and we computed those, and what happens is that on this regular part on M circ, for instance, the Bismuth-Ricci connection with respect to J is 1/1/2 DDC log determinant of this Hermitian symmetric matrix that we got. And if we do for I, we have to change B with minus B from the general correspondence, but the determinant of Hermitian symmetric matrix is real, so it's the same. It's the same expression. So we can. So amazingly, we have this common function, common Ricci potential for rho Bj and rho Bi, which is very, very nice. This is an observation which we don't know how to prove in general. For instance, that there exists such a function which is a common Ricci potential for bottom line on some open lens subset in the manifold. Marco may have ideas about that. I think we already exchanged some questions about this fact. So now I will add the final condition. The final condition on toric geometry is very well known, and from the symplectic point of view, it simply reads that you have a preferred barycenter for your polytope. And since these momentum images are defined at translation, we could assume without loss of generality that the origin is this barycenter, and the barycenter means that the value of the affine linear functions defining your polytope at 0 are all equal to 1. They're equidistant from the origin, if you want. And this 2 pi C1 normalization means that this equidistant thing is equal to 1 in terms of the corresponding polytope. Now, I will use this condition to make some sort of a calculus observation. If I take this Ricci potential that we saw before for the Bismuth-Ricci, the common Ricci potentials for the two Bismuth-Ricci tensors, and if I subtract this Legendre transform of U essentially, this is precisely the Legendre transform of U, I will get something which is smooth. So for this to hold, we use the boundary conditions of U together with this condition actually. If you work it out, the calculus argument that this is a smooth function, you will see that you use in essential way this thing, plus the boundary conditions that we had before. U minus UC is a smooth function, essentially. That's what you use. So this will be crucial for the next slide, for the slide you see right now. Actually, I will now define a flow of symplectic potentials, UT, by imposing that the T derivative of U is twice HUT E minus 2 times T B0. I just sort this out from my pocket, this equation. Well, I guess we guess it really and prove it that after identifying. So this is okay. So this is a flow. So you see, this is a flow of symplectic potentials for the moment, as I defined it. But what we claim is that now, if we consider on top of it the A0 and B0 deformations of this very particular form, then we get now a flow of generalized scalar structures of symplectic type, toric generalized scalar structures of symplectic type. And we claim that after identifying the corresponding complex structure JT of this guy with a fixed one, with a canonical one, let's say, we get precisely the normalized J fixed generalized scalar Ricci flow. So the upshot of our findings is in this proposition that in the toric situation, we could reduce this generalized scalar Ricci flow to some sort of a scour PDE, but in terms of the symplectic potential, which once again is not a smooth function on the whole manifold, only on the regular part. So this has to be a little bit worked out, a little bit more to get our general idea of this scalar reduction, the generalized scalar Ricci flow. But that's the key technical result which we proved.
Is it obvious that the generalized scalar condition, you have this condition of Hessian plus Hessian of U plus I B? Yeah. So is it obvious that this is going to be the condition on the faces is going to be satisfied for the solution of the PD?
Yeah, so that's a good question. But remember, we had U minus UC smooth plus some kind of open condition on the interior of each face. That's strictly convex on the interior. So for small t, for small amount of time, the second condition will be satisfied, and the first condition will be satisfied because because U0 has this right asymptotic behavior with respect to UC, and since this is a smooth function, that was my previous remark. So this is a global smooth. So this is a global smooth function. That was my previous remark. Because this is a global smooth function, then UT will also satisfy the. Yeah, it's a good question, but you can figure this out directly from the previous slides. That the right hand side is smooth, globally smooth. Will tell you that for a small amount of time, this will be satisfied.
Thanks.
Okay. So one striking observation is that this flow, if you look at it, A0 is completely ripped off, so it's completely detached. It doesn't depend on A0. So if you want to study global existence, you could actually assume that A0 is 0. And we will do that. Now, assuming that A0 was 0 or A is 0 along the flow, we are in a very favorable situation because we will have we don't have A-type deformation, so we really have that the fixed complex structure J will be the Keller one, the one corresponding to the symplectic potential. So we don't need to do the Boulanger type deformation of the complex structure at the first stage. So we only deform the symplectic form. So this is very favorable because this U will define a Keller metric. Okay, omega bar, and what we are doing is just we are deforming this Keller form omega bar, initial Keller bar omega bar with constant with this constant Bij d mu I d mu j. And if you look at this deformation, you will find out explicitly that it solves the Yau equation. So omega bar m will be equal to Fm because Fm is omega bar, which has angular momentum coordinates. So it's anti-diagonal when you add something which is just upper block, and you have this condition just essentially for free. So in this, so we want to study the flow globally. We could reduce to a equal to 0. All the properties are the same of the initial flow. And when we reduce to a equal to 0, we have this Calabi-Yau condition for free. And we have a explicitly related omega bar and F. So that's the important ramification. So in the previous slide, you saw that we have a flow on symplectic potentials, but we want rather to find eventually a flow on relative Keller potentials, which was our promise. So to do that, we will do a two-step process. So first, we will rewrite this flow in terms of the Legendre transforms. So the Legendre transforms, which I know phi t, will satisfy. So this will be essentially. I'm probably missing. I think I'm missing some coefficients. It's one. I think it's twice here. I have a missing 2. Sorry about that. But yeah, when you do the Legendre transform, this will become twice phi t, and dot ut will be minus dot phi t. And I rewrite just the same thing in terms of the Legendre transform. Why I did that? Because remember, the Legendre transform was the device that gives me the relative Keller potential. So the upshot is that we have 3 equivalent ways to rewrite this flow. So one is in terms of symplectic potential, where we fixed a symplectic form, and the second way is just in terms of this Legendre transform. And now we will use that the Legendre transform leads us to this relative Keller potential phi t as before, and we end up with a scalar reduction in terms of the relative Keller potentials, which is a very nice. So we can write it in this form. So I will probably spend some time to define thoroughly the terms. So the first term is precisely the term that we saw in the Keller reduction in the final case. So if this second term was gone, it will be precisely the Tsao reduction of the Keller-Ricci flow in the final case. But this second term has geometric significance. So this omega bar m phi t, remember this was f phi t to the m as well. And so this is the volume form of f divided by the volume form of the pluriclose metric omega j actually. So the 1-1 part of A is omega j. So this term in terms of generalized scalar geometry is very natural. This is once again the volume form of the symplectic form divided by the volume form of the Keller form of the generalized scalar structure. It's important to notice that it has sign, this term. This term is always positive because the volume form of the symplectic form tames J, so it's strictly greater than the volume form of the pluriclose of omega j. And what I put below is the general way to define this geometric form. So this is the Keller metric defined in terms of the relative Keller potential, so omega bar phi t. And I can, from what I said before, I can write the symplectic form defining our generalized scalar structure. It's f phi t, which is given by omega bar plus e minus twice t omega bar p b0 omega bar, where p is this is a real Poisson structure corresponding to the B-type transformation. So I saw this formula in the talk of Francis. I don't remember where, but I'm pretty sure I saw this this precise formula in the talk. So it's, to me, it's very interesting to understand a little bit more the geometrical meaning of this. So you see, omega bar is a Keller metric with respect to a fixed complex structure. F now is a symplectic form taming a fixed complex structure and defining a generalized Keller metric. So we define essentially the Keller structure by this very interesting way, composing by a real Poisson vector, which corresponds to the B-type transformation of Wong. Anyway, for instance, this formula implies that F is closed, which is not obvious at the first place, but you can work it out from here. So here is the conclusion. The conclusion is that we can think of the generalized Keller-Ricci flow as a flow of Keller metrics related, naturally related. So this essentially is the scour reduction of the flow of Keller metrics, omega bar phi t. And if we know this flow of Keller metrics, we can recover the generalized Keller-Ricci, the normalized generalized Keller-Ricci flow by doing precisely this algebraic manipulation. And it's equivalent to study one or the other. Now, I want to very quickly finish this lecture.
One question.
Yeah.
Fixing A, does it have any geometric meaning? Or
which one?
Fixing A. You said A equals to 0 in part of your discussion. Does it have any geometric meaning, or?
Maybe. Maybe. I think what it would mean for us I'm not sure. Yeah, we saw the significance when we tried to define some functionals. But yeah, that's a good question. I don't think I will answer something intelligent just right away. But I think there is something to do with the fact that if you restrict F to the real part of the holomorphic Poisson structure, you get 0. I think some kind of also one way to characterize it, and it's quite it's important in geometric manipulations. But yeah,
I guess it's also true in the setting, right, that the A type deformed complex structures are biholomorphic to the
all A and B deform,
just like a gauge action somehow.
Yeah, that's true. So if you deform, if you do A type deformation, you can do the same thing as in this Lerman-Thoman argument to kill this, but it has a geometrical significance, as I said. It's so this reduction would not hold in general if you didn't suppose A equal to 0. So this explicit way to connect to the Keller reduction. So we have generalized Keller-Ricci flow. To get the Keller reduction explicitly, we use that A is equal to 0. We can always do that because we know that up to A type transformation, which is exponential minus 2 times t is 0 at each given time, we can always reduce to such modified generalized Keller-Ricci flow, and then we can reduce to the Keller-Ricci flow. So it's revertible, but still it's important to assume A is equal to 0 to get the correspondence explicit.
Okay, thanks.
Yeah, and here is so our first result is a long time existence. So I will very quickly go through the steps. So it starts us in the Keller case. We will first see that for finite time we can elaborate C0 bounds for phi dot and phi. It's just out of the construction. You take another derivative in the defining equation here for this phi t, and when you linearize this operator, you miraculously find the Chern Laplacian of the generalized Keller structure applied to phi dot minus twice the norm of the skew symmetric part of F and J. And from here you have a maximal principle. So you see that has a sign. So exactly as before, we will have one side control of phi dot. But now, without any toric assumption, just the symplectic flow and some evolution formally, you can see that this norm in general, the hit operator to this norm of the skew symmetric part has a sign. It's completely for any. That's true in general when you consider generalized Keller-Ricci flow of symplectic type. So this guy, it's uniformly upper bound. So combining with the previous, you get a bound from below. And as before, this will give also a similar bound for phi t. So this okay. So this essentially yeah. So this is the first step. So we have these bounds. Now the second step is that we have to improve this to finite time C0 bounds on the metrics along the flow. So it's only in potential, but I have to take a DDC of the potential to get the metrics. And so I have to elaborate a little bit more on that. So here is the potential control, the potential PD. We found that this is bounded at finite time. This is bounded at finite time. This is globally bounded because it's a constant function. So the sum of these two terms is bounded at finite time. So the next step is that we saw already that this term, the additional term from the generalized Ricci, from the normalized Ricci thing, it has a priori upper bound, just because omega to the power m or omega bar to the power m is the same as omega to the power m f to the power m, and this is less real than 1. But it also has a lower bound, and this is again not a toric phenomenon. In general, for generalized Ricci flow of symplectic type, you could actually elaborate the evolution of this quantity in general. So this will be the FTM in general. And it turns out that it's this Chern Laplacian plus this time a positive term. It's essentially the norm of the torsion. So this miraculous thing gives us, with maximal principle, gives us a lower bound of the logarithm, and we have an upper bound already. So this means that this term is bounded as well. So it leads us to the conclusion that this term is bounded. I'm not an expert, probably Jeff will know, but even at that point, it seems to me that with Yao estimates, we could probably conclude, but we did something slightly different. We went a little bit further, and we actually used so this term is bounded from C0 bounded from above and below. Now we want to also bound the trace of. Okay, so before I proceed, so we show that that this term was bounded, and if we compute the trace of omega bar t with respect to omega t, so the Keller reduction with respect, so we use the toric condition here, I believe. You will get that it's m times this norm that we already saw it's bounded. So the trace is also bounded. So this means that actually the Keller reduction and the actual generalized Ricci flow are comparable. They are quasi-isometric. So we could establish this C0 inequality of the metric with respect to the generalized Keller metric or with respect to the Keller metric, as we wish. I probably will do with the Keller metric in the remaining arguments. So we already saw that the determinant of this term is bounded. So it's enough to show that the trace is bounded to get this, the C0 bound. And this is again with the maximum principle. I believe that we did this in a previous paper with Jeff, this computation, but the trace of omega t with respect to a fixed background metric was computed. It satisfies for a big enough an inequality of that sort. So this a priori estimate was recycled again to get this trace here is upper bounded. With the bound of determinant put all together, we get the promise bound for the metric. So what we said now, if we have this bound C0 bound at finite time of the metric, now we fall in the machine from Jordan and Streets. You can derive a higher order estimates at finite time. And once we have that, we fall in the machine that Jeff developed. If we have the higher order estimates at finite time, then this generalized Ricci flow system will be prolonged beyond any given finite time, and therefore the flow exists for all time. And few words about theorem 2. So we have long time existence by such arguments. And we want to prove some sort of convergence. So to prove some sort of convergence, we use variational methods. That's what so actually in Tian Zhu arguments, they use C0 estimate. We don't have C0 estimate because we don't have even Perelman type estimate for this modification of the PDE. So we use some kind of a more recent techniques in Keller geometry which overcome the C0 estimates and prove weak convergence in the Keller case. So we will do the same idea. And these techniques use Mabuchi functional, Mabuchi energy as a functional to which some compactness will be applied. So now we are in a toric situation, and we know how the Mabuchi energy of a toric Keller variety is written, and that was very easy to guess how to modify it to define a Mabuchi energy on a generalized Keller toric structure. And here is an explicit formula. So you take the symplectic potential, you integrate it over the boundary of the polytope with the induced measure from the defining facets. And you divide by some integral. So this is essentially the Futaki invariant that's extended to continuous functions instead of a fine linear. And there is this so-called entropy terms, which is the log determinant of our favorite term, plus log determinant of a reference metric. So you can see from the boundary conditions that this difference will be integrable smooth function actually on the polytope. So this is for A and B fixed, gives you a functional which gives to any general scalar toric metric a finite number. If B was 0, this is the usual Mabuchi functional expressed on toric variety. I think Donaldson first found this beautiful formula. And so I define it just by analogy. So what are the critical points? If you do integration by parts in this definition and play a little bit, you will find that the critical points correspond to this kappa UIB expression being equal to constant. And this kappa UIB expression is given by a very nice formula. So what you do, you take this Hessian plus square minus 1b, you invert it, you take the real part, which I denote by x, it's a symmetric matrix, and you take minus xij, derivatives ij. It's a very similar to the Brio formula, in which case, in the Brio formula, there is no b, and you get just the inverse Hessian. And this expression is shown by Wong to be precisely equal to the moment map found by Boulanger and Professor Goto. So this is precisely the scalar culture that Professor Goto described in more general case, but here in the toric setting, this Mabuchi functional, the critical points will be general scalar structures with constant general scalar curvature. So everything is very nice and exciting. So it's really extends very nicely to what should be. But now we turn to our problem of global convergence of the Keller-Ricci flow and how this Mabuchi energy will be relevant. The main observation, which took us some time to prove, but it turns out that this Mabuchi energy is monotone decreasing along the generalized Keller-Ricci flow. And that's the key thing. Now, we have a pre-existent machinery. We know that if there exists a Keller-Einstein metric, then the Mabuchi functional, but non-modified. So here we took A equal to 0 and something, but now we'll take A and B equal to 0. So the usual Mabuchi energy is coercive. It's coercive in the sense that there exist universal constants, lambda and delta positive constants, such that if you calculate the Mabuchi energy with respect to some u, it's less Ricci, it's a bigger Ricci lambda, the norm of a normalized. So we normalize u by adding a fine linear function such that the origin is the minimal point of u, and it's equal to 0 at this minimal point. So there is a unique fine linear function for a given convex function which satisfies this condition. So we normalize u's by this way, and then you have this coercivity property. It's proved in the toric setting, I believe, by Zhu and Zhu. But it's also now proved in more general setting by Tian and Darvas and Rubinstein. So it's a very well-established result for the existence of Keller-Einstein metrics. How it's related with our modified Mabuchi functional? The point is that our modified Mabuchi functional, if you look at the definition, so determinant of this guy is strictly less than the determinant of the Hessian without the B. So we have an obvious inequality. We have an obvious inequality, which means that the modified Mabuchi is always greater or equal than the unmodified Mabuchi, and it pairs very nicely with the coercivity property here. And moreover, Mabuchi is monotone, decreasing along the flow. So if you put all these facts together along the Ricci flow, you will get that MUT will be less or equal to B0 minus, well, with some B. So here is without B, here is with some B. And this will be less or equal with than the initial value. And it will be greater than the whatever is the coercitivity factor sum. So in sum, you will control this one norm of the normalized potentials. This is, of course, not enough to get weak convergence. But the good point is that when Mabuchi is controlled, when Mabuchi is bounded, there is a general technology, a recent technology due to Darvas, Berman, Buxton, Getz, Zeriahi, which use pluripotential theory and weak compactness results. And essentially, if you apply these results thoroughly in this situation, you end up proving that this normalized symplectic potentials will converge in L1 of the polytope to a convex A1 function on the polytope. So that's the weak convergence in the statement of theorem 2. So I guess I can stop here. So I give you some kind of a flavor of what we are doing. So this last part is not trivial. It really uses kind of deep results, recent deep results in Keller geometry to get to the weak convergence. But this inequality gives you the plausibility already that this would happen, because L1 will be controlled. If you have a almost everywhere convergence, then you have an L1 convergence, and that's what's going on actually.
Thanks, Vesti. Are there more questions?
Yeah. So you are working in arbitrary dimensions, right?
Yes.
So then, is there a formula for this generalized scalar curvature in terms of the Hermitian data? You said that this is the generalized scalar curve.
Yeah, in the Torrey case, that's it. Yeah, that's it was found. So this formula was found initially by Boulanger for eight.
This was in 4 dimensions, right?
No, in any dimension.
Oh.
Well, there is a GIT picture in the Torrey case, which is specific, a little bit specific to the Torrey case, which Boulanger developed. This GIT picture has been extended by Professor Gotto to much more general class of, so you don't need a symplectic type anymore. Even for any generalized scalar structure, there is a GIT picture. So in general, Boulanger computed the moment map, and he found this formula in the Torrey case. Professor Gotto observed that his definition of the scalar curvature is the momentum map in general. But since there is no an explicit link to bi-Hermitian geometry, it's still not clear if these two expressions coincide. They coincide up to some constants, but whether they're. And I think Wong went to check all the details that they actually agree on the toric manifolds. And yeah, in the Torrey case, one advantage is that we have this very explicit expression.
But this kappa that you have here, this can be written explicitly in terms of the big Hermitian data, right?
Yes, it is already, because I see what you mean. Yes, this can be also done. And I think we did it when writing the paper, but somehow we didn't find the use of it. But yes, it can be expressed in terms of bismuth curvatures and Lie-form norms. And unfortunately, there will be this difference of volumes, this symplectic volume against the Riemannian volume. so this P function would, in Boulanger's paper, there was this logarithm 1 minus P, this, if you remember. So this logarithm 1 minus P function will pop up everywhere. And we didn't went too far to get a nice formula, but yeah, it could be done. Everything it's available now, yeah. I believe even in this could be done. I hope I not commit something, but I think we can do that in the symplectic type case. I believe so. We could make a closed formula in bi-Hermitian data of, I have to be careful. Yeah, in the third case, for sure, we can do that. Yeah, so the idea, as you see, is that this Mabuchi has also expression in bi-Hermitian data, close expression, and you could find the critical points directly. And you get an expression in those terms that I just mentioned.
And this weak limit that you get, does it have some meaning as some sort of singular constant scalar curvature?
Yes, that's a very good question. Yes, it has. Actually, for the purpose of some clarity, I put it that way, but actually it's a limit of currents. So it will be a current. It will be a current that you could wedge, what we call of maximum Monge-Ampere mass. You could wedge it, and we want to show. One would expect that this current would satisfy some weak PD. Actually, in the Keller case, when you prove that it converges to a Keller-Einstein thing, the argument is that this current that you define from the compactness arguments of the Mabuchi will moreover satisfy a current version of some Monge-Ampere equation. And there are regularity results for these things now available. However, to obtain this additional weak PD, you have to use the Dink energy. So there is an argument using that Mabuchi and Dink energy converge to the same thing along the generalized Keller Ricci flow. We cannot yet claim that. So we have an analog of Dink energy, but we cannot prove that it converges to the same thing as Mabuchi, and therefore to some kind of a weak Monge-Ampere. So we cannot show that this current will satisfy a weak Monge-Ampere equation yet, and use the regularity machine to say that it's a Keller-Einstein metric. But that's what we expect, of course. Yeah. So far it's just a current, which, however, has a maximal mass and finite energy. So you could write in general Monge-Ampere for this type of currents. So.
Okay, thanks.
Okay, any others? Okay, well, if not, yeah, let's thank Vesti again. Thanks.
Thank you. Actually, I can even